So thank you. My presentation will be about a recent package in Julia, which is ORTools.jl, which is a way to get access to Google solvers within Julia. So this is the French edition of a talk that took place at the JuliaCon this July in the US. So first, just because I'm not sure everyone in the room is really aware about what you can do in operations research, so I'll recap a bit what it's about. So one way of seeing what operations research can do for users is those 5 gerunds, which is just a way to say what kind of problems can we tackle in operations research. One of the first family is scheduling. So in what order can you execute the operations in your data pipeline? You can also have planning problems. So how many machines should you have to meet the growing demand for compute in your organization? You also have routing problems. So for Google, that could be to generate the Google Street View images. So how do you route the cars to get the best images in the least amount of time? You also have assignment problems. So when you get a new query, well, what web server should answer that query? You also have finally packing problems. So when you have huge boats, how do you pack the containers on that boat? So all of these problems are instances of what happens at Google at some point. So that's originally why Google really needs an OR team. All of these problems are NP hard in some sense. So you just can't throw any kind of algorithm at that and expect to get great result in good compute times. So more specifically, the OR team at Google is divided in 2 parts. There are people that work really on close to applications and those that work on lower level solvers. But initially, the very first application was routing for Google Street View. So we have a quite generic routing solver that you can use for any kind of logistics application. That's open source on GitHub. You can download it. It's really the main driving factor for people to use OR tools. And you also have an API that you can use. It's freely available too, is JuMP. We also have people that work on concrete applications, such as workforce scheduling or shipping network design. So it's really concrete things that, well, with words that really map to instances in the world. We also have people that work on lower level solvers. So we have Glop, an LP solver based on the simplex. We have CP-SAT. That's a CP solver with a lot of SAT elements that won a lot of gold medals at amazing competitions. So it's really competitive for quite important problems. We also have PDLP, which is a first order method to solve LP problems. So we have the original implementation, then you can see the same algorithm basically in many solvers in the world. And also something that's really the core of the presentation today, MathOpt. It's a modeling layer that you can use to access all of these solvers within OR tools. So all of these elements are available in one open source project, which is called OR tools. You can use it in many languages, mostly C++, then many parts in Python, in Java and C#, and now a few parts in Julia. So here is a brief outline of my presentation. I'll continue diving into the topic of operations research to present the basics of what you need to understand to really grasp the presentation. Then the link between this MathOpt modeling layer and JuMP in Julia. Then I'll also briefly talk about the development hurdles of bringing OR tools to Julia, because it wasn't really a smooth journey. And a few hints about what's next for this package. But first, a bit of mathematical optimization. So it's one part of operations research, and it's really the crux of OR. So it's really making the distinction between the problem that you have to solve, or your data, and the algorithm. So you have solvers that implement simplex, local search, or whatever you can imagine. And then you have your problem, which is one specific case of scheduling. So to define this problem, you need 3 parts. First, the decisions that you want to make. So do I make this operation before another? You have constraints to respect. So maybe you have to do some tasks before some point in time. And a goal to achieve, which is usually minimizing costs, but for scheduling, it's also quite often minimizing the total time of your operations. So in this sense, you're no longer programming in a usual way. It's really declarative. You say what you want to achieve and not how you want to achieve it. And then, depending on exactly how you formulate these decision constraints and objective, you can have linear programming, mixed integer linear programming, constraint programming, and so on. So to be a bit more explicit about what these words are, here are a few examples of what you can have for variables, constraints, and objective for problems. So the first example is scheduling. So a variable could be, when do you perform the first task A? Is it the first one or the second one? A constraint could be, you have to perform task A before task B. So the time at which you perform the task A must be less than the time you perform the task B. And then you have the objective, which could be to minimize the time that you take to perform the last task. It could be also planning. So in that sense, when you have some amount of compute to reach by buying new machines, then your variables are the number of machines that you buy. The constraints is deploying some amount of compute. So say I need 5 terabytes of RAM because I know my application. And your objective is maybe to minimize the total cost of serving this demand. So now I'll get into the next step, which is to get computer code out of this quite abstract thinking about your problems. And that's why you get some Julia and JuMP. So for now, we focused on the first step, which is modeling your problem. Then you're getting more technical, and you can go to Julia code using JuMP to really formulate your problem as code. Then you give this model through a solver, which is typically C, C++, Fortran code, to solve the problem. And the solver gives you a solution. And where ORTools comes in is really for this solving part, where you have a lot of solvers for your problems. So here is one example of an optimization model in Julia using JuMP. So it's a quite basic least squares model. So well, normally it's nothing really too fancy. So you first define your optimization model, then you define your variables. So that's your linear model and the residuals for each of your data points. Your constraints can be just defining the residuals based on your data points. And your objective is to minimize the total square error. So that's what a user can write for optimization models. But then you have to make the link between this and the solver behind. And JuMP uses an interface that's called MathOpt interface. That's much lower level, and that makes the link between what user sees and what solvers see. So while JuMP is made to be easy for humans to use, MathOpt interface is easy for solvers to, it's at the same level as solvers. So it's easy for solver writers to write. So as you can see, it's not exactly as abstract as before. Just defining a constraint is much harder. You don't have access to anything with metric terms. And I see Eva that really agrees with that. But, well, here, MathOpt interface is really just an interface. And it does not do much by itself. So it's mostly just a contract, a way to write your programs so that JuMP can talk easily to the solvers. And that's where we're really talking about ORTools and its MathOpt component. So MathOpt is roughly the same thing as MathOpt interface. And you might have thought that because they have similar names. So both of them are modeling layers. The difference between them is that MathOpt is part of ORTools and it gives really easily access to all of your solvers. So it's one way to access all of ORTools solvers. It's one way to solve models remotely using Google interface. So it's really the first step to bring ORTools solvers to Julia. MathOpt is based a lot on protocol buffers. So it's not the same kind of interface as MathOpt interface because it's purely data. So it's just like JSON on XML file. It's really similar to that. except that it's the Google version that's extremely optimized for a lot of operations. MathOpt also has a C++ interface that has highest performance, but C++ and Julia do not match that easily. So for now, we're focusing on protocol buffers. So just before diving really into the Julia package, here is an example of the C++ interface in MathOpt. So this is what the same model I showed you before would look like using MathOpt. So again, it's quite different. So there's a small part between quotes that I just don't want to show on the slide because it's going to be too long. So although it's more or less the same level of abstraction as MathOpt interface, it's a lot harder to use. And we'll see that in the Julia package too. So this Julia package, ORTools.jl. So for now, it's mostly a wrapper around ORTools MathOpt, this modeling layer. So with that, you can have access to all of ORTools solvers, which include CPSAT, Glop, PDLP, and possibly others later on. It also gives you access to other supported solvers. So you can use it to access Groby, GLPK, or Skip. In Julia, it's not really useful because you have direct access to these solvers, but in case, you can still use them through MathOpt. So the main goal of this solver is to give access to a lot new solvers that you just cannot support otherwise. And it was not exactly easy. So there are quite a few technical challenges, but not only. There are also organizational challenges because, well, no one really uses a lot of Julia at Google, so there's no internal push to develop these interfaces. And overall, Julia is not really a priority at Google, so we will never have the same level of support as our Python, Java, and C# bindings, but still we can do something nice. But then about the technical challenges. So C++ is not as easy to access from Julia as C code, because just C code, you just type one line and you get access to your C API. For C++, you have to wrap a lot of things. And the problem for us is ORTools is mostly entirely written in C++. So that's why we decided to go with another route, which is to use the protocol buffers interface and a very small C API. So it just something like 5 C functions that you can use, and you have the same access in terms of feature to ORTools. Also, ORTools is really easy to build using CMake, but it's a really bespoke CMake that works very well for our purposes, and we developed it for the last 10 years, and it's not exactly how Yggdrasil and Binary Builder expects CMake code to work. I'll speak about it later on. Then on the Julia side, there were two major challenges. So there's an implementation of protocol buffers in Julia, which is very nice, but it's not as easy to use as in other languages. The major problem is mutability, but again, I'll get into the details later on. And also, that was a challenge that we really expected from the start, is that MathOpt interface is really a hard interface to implement, but that's how it is. So CMake is the de facto standard to build C++ code. Basically, every project uses CMake in the open source world. And we have a huge CMake infrastructure to build ORTools to make all of our releases using cross-compilation from virtual machines and so on. So it was extremely well for all other purposes. But that means that, for instance, for cross-compilation, we have a lot of things that are really custom, because our protocol buffers are based on code generators. So that means that during compilation of ORTools, if you're running the compilation on Linux and you target macOS, for instance, that means that you have to build a binary for Linux to compile the protocol buffers part and to compile the end code for macOS. So you really have to make the distinction that there are many ways to do that in CMake, and well, ORTools and Yggdrasil are don't really agree on that. So that was one of the problems that you have. There's also the problem of supporting some platforms. For Julia, ARM is defined in a slightly different way as ORTools. So that means that we absolutely need crypto extensions from ARM platforms just because of a dependency. Most people that will use optimization solvers will have those extensions, but Julia decides that ARM is not defined with these extensions. So what do we do in this case? So that's why we have to tweak a lot of things for the binaries that we release for Julia. Then about protocol buffers. So it's really the Google way of sharing data from process to process. And it's one of the major interfaces of MathOpt. So hopefully for us, we got at least protocol buffers. So for instance, that's how we wrote Java bindings. So if you want to use MathOpt from Java, you will internally build some protocol buffer file, then send in to our C++ code just using this small C interface. MathOpt also has a huge C++ interface, which is the way to go really if you want the best performance, but it's hard to use. And something that happened during the development of our Julia package is Elemental. So it's a new layer that's a very small and orthogonal C API that you can use to access all of MathOpt features. And well, it's so great that for now the Python interface uses this C API to access MathOpt. So that means that we're talking about 3 languages to target the same library, and we're using 3 different ways to use that library, just because of how things develop over time and what's easy to access from one language to the other. Then the Julia part of protocol buffers. So it's a code generator also in Julia. So you generate a bit of code to access this binary file. And in practice, well, there are very, very few users of protocol buffers in Julia. Just a few users that target gRPC, but well, we didn't know at first if that was a viable option just because barely anyone uses protocol buffers in Julia. But we had that great surprise that in practice it works very well. It's quite strong. There were a few bugs that were ironed out just before we started using it, so timing was perfect in this sense. It was a bit hard to use just to define the path when you're compiling the code, but well, that was one day of work. So really, it was quite easy to use. Not as easy to use as the C++ protocol buffers with CMake because, well, it's just one line of code and you're done with it. But in the end, it worked very well. But the really missing feature in protocol buffers in Julia is mutability, because we're trying to build structures really bit by bit. And for that, it's really much better when you have mutable data structures, and the Julia code is immutable. So that means that to change one field, you have to copy the whole thing. So what we're doing currently is to duplicate code instead of copying a lot of data at runtime. So it's not great, but it works. We have a PR that's open for protocolbuffers.jl, but it's not yet merged. So we hope to get that merged. So we will have a much better package in the end on our side. So that was it for the development hurdles. So a few things about the future of our Julia package. So you currently have access to all solvers through MathOpt, but that's not always the best way to have access to your solver. So for Glop, that's great because it's a linear solver. MathOpt interface is made for linear constraints. It's great. CPSat, on the other hand, has a MIP part, but also CP part. So you have a lot of constraints, such as all different, and you cannot use them using our MathOpt. So that's work in progress to provide direct access to CPSat. We also have the PDLP solver, but if you're using protocol buffers, then it's a bit useless because with protocol buffers, you're limited to 2 GB models, and PDLP starts to be useful at 2 GB because it's remade for huge models. So we'll have to do something else for PDLP. There's also a feature about remote solves. So you're using MathOpt on your computer, but you don't solve locally. You just send that to your Google server. So we currently have designed this part. It's not yet implemented, but it's going to end in the package soonish. We also have a few parts where we could improve our implementation, mostly to have it faster. So that could be using this elemental C API for local solve instead of building a protocol buffer, then process communication. We could also use the C++ interfaces if that's faster, but that would mean writing a quite large but easy to write wrapper for this C++ code. But there's something that's maybe more groundbreaking for ORTools. It's other kinds of solvers. So for now, we focused on MIP and CP solvers, but that's not all what ORTools has to offer. We have a huge routing solver that many people really like to use. And it's really hard to bring to Julia because there's no usual interface for routing problems. So we'd have to write our own from scratch. We also have more dedicated solvers such as bin packing. And it's the same problem. There's no usual interface in Julia, but we have them. And maybe people would like to use them. So that's one part where I'd like some feedback. It's really, would you like to access those solvers? And that's all I wanted to tell and ask you for this presentation. Thank you.
Thank you for the presentation. It was pretty amazing. A bit on the protobuf.jl, there is a quite esoteric alternative that goes through Go. Go has great support for protocol buffers, and it also compiles to shared objects. Have you considered going through the Go route? And I don't know if ORTools supports Go, but it could be a nice workaround.
So your question is really about using protocol buffers just to cross the language to go to Go and then to go to our solvers. That's right.
Yes, because you can build a C interface from Go and load it as a shared object.
But actually, we're using the same C interface as Go. So it would be just to add one dependency on Go and bringing no benefit.
You would skip the protocol buffers in Julia.
Well, you'd build them in Go.
Yeah, I mean, it's already there.
But I agree that really the Go protocol buffers are much more reliable because it's battle tested on server code. But for now, I mean, this Julia interface really fits our needs.
Okay.
But yeah, we don't know how reliable it is.
Yeah. Okay. Thank you.
Another question? Maybe one then. Did you consider also maybe splitting out PDLP to have its own separate interface, being able to provide the data directly instead of through protocol buffers?
Yeah. So that's really how you're supposed to use PDLP. And to use, well, currently it's a C++ interface, but we can write C API just to target it.
I see, okay. Yeah, because otherwise the 2 gigs of limitation for PDLP precisely is the place where it should not be, as in it's the place where you want to chuck a whole lot of data to.
Yeah. So that's why we're trying to cut that part for later release.
Hi, thanks very much for the talk. I just had one question. What prompted you to release ORTools for Julia? Do you have Julia users at Google?
Sorry, could you repeat the question? I just couldn't hear the first part.
What prompted you to release ORTools for Julia? And second question, do you have Julia users at Google that would use this release?
We have a few Julia users, but they're really usually targeted on some applications. So overall, well, it's not really worthwhile just to target them. So it's more to increase our potential user base.